Yeah, now we are going to look at an family known as adiabatic logic. Okay, now for certain applications like biomedical applications or RFID tags and things like that, where power might be an for IoT sensors and all, which you have implanted here and there, power could be an issue. There could be limited power available, right? If some sensor is embedded into a human being, you can't have a big battery also, right? So it has to, the power available is very minimal, right? But the frequency of operation can be very less, right? Even if you are operating in kilohertz, it is milliseconds. So suppose you are taking sensing the temperature of human body and transmitting it continuously for monitoring purpose, right? The temperature need not be sampled at gigahertz frequency, right? Even if it is sampled at kilohertz or even lesser also, it is fine, right? But power is an issue, right? You can't have a huge power bank implanted onto human beings. Similarly, for many IoT sensors, and there are several applications where power power is a major issue, whereas frequency is not an issue. So in those cases we use adiabatic logic. So what is an adiabatic logic? Suppose this is a static inverter. Okay, just consider this as an NMOS and PMOS, although TFETs have been shown here. So just consider this as an inverter. So this we saw whenever the input is like the input is going from a high to low. So in that case, this node will be charged to VDD, right? And then we saw the energy which gets dissipated in this PMOS is VDD square CL by 2. Right, this is what we learnt in the, if you remember, the very first class which we did, in which we saw that the power which gets dissipated is VDD square CL by 2 in the PMOS, and VDD square CL by 2 is the energy, this is the energy which gets dissipated. If you multiply it with frequency, you will get the power. So this is the energy which gets dissipated as heat in the PMOS, and VDD square CL by 2 is the energy which gets stored in this capacitor, right? Now instead of that, if I charge this capacitance in 2 steps, okay, I am giving an input voltage, but VDD, after giving the input voltage to 0, I am giving VDD. Instead of giving VDD here, I initially give VDD by 2 and then I increase it to VDD. I am giving it in 2 steps. Then what happens? So obviously in the first go, VDD square and VDD by 2, right? So VDD by 2 square CL by 2. So that will come to VDD square CL by 8. And in the next step, again it will be VDD by 2 square CL, okay, by 2. That will come to VDD square CL by 8. If you add up, you will get VDD square CL by 4. Now if you see, if you are increasing the VDD in 2 steps, okay, the total power which gets dissipated in the PMOS reduces by 50%. Is this clear to all of you? Right? Now instead of, if you have now normal switching inverter, so this is the power which gets dissipated in the PMOS, right? So if you have a normal inverter, if I have a VDD apply here, so this from VDD, this gets charged to VDD, right? In that case, VDD square CL by 2 is the power which gets dissipated in the PMOS. Okay, now instead of doing that, now I am giving a signal out here, right? I am giving initially VDD by 2 and then I am giving a VDD here, right? I am giving this power supply in 2 steps here. Initially I am giving it at 0 here, okay, and then I am increasing the VDD to by half here, okay, and then I am increasing to 1 here. So if I put in this equation VDD by 2 here for the first half cycle, the power which gets dissipated is VDD by 2 square, right, 4, and then you have one more in the 2 in the denominator, so it comes out to be VDD square CL by 8. In the next step, again again I am from VDD by 2 to I am going to VDD. In that case also the total net change in VDD will be VDD by 2. So it will be VDD by 2 square. So that will come VDD square by 4, and this is another 2 is already available here. So it will become VDD square by 8. So if I add it up, so I will get VDD square CL by 4 out here, right? Now instead of making this in 2 steps, I make it in n steps, right? So it will become, so the total power dissipated in PMOS will become VDD square CL divided by 2n, okay, where n is the number of steps, right? And instead of step, if I increase this VDD as a slow ramp, okay, then the power dissipated in PMOS will be negligible, right? So now one way, so this is the mathematical analysis for that, okay. But if I have to physically try to understand what is happening is, if I slowly ramp up this voltage out here, okay, and allow a current which is flowing like this, okay, but since I am ramping up this voltage slowly, this voltage also will ramp up slowly, and if these two are able to follow each other, okay, very close to each other, okay, so because the ramping up frequency is very, it is not a steep, it is on a slow frequency ramp up, this node voltage also will follow this voltage out here, because I am giving a 0 here, so this PMOS will. So if you see here, a current will flow, definitely a current will flow like this to charge the capacitance, like, right? So the half VDD square CL energy will be stored here, but there will be no heat dissipated here, because the heat dissipated is proportional to the IV, right? So I is there, but V is not there. You are allowing the drain and the source voltage to follow each other very close to each other without any propagation delay because of the slow operation. So that is why there is no heat which is dissipated here. If you give an steep signal out here, okay, if you give a step signal here 0 to VDD, so initially this will be 0, this will be VDD, so there will be VDS and VDD drop across this PMOS transistor, and there will be a current also. So you will have the current into voltage, okay, that will be a big factor, and then you will have that much of heat being dissipated. Here the current will flow, but from the potential between these two will be close to 0 out here. So that is the reason we are allowing this voltage, this source voltage to follow the this drain voltage to follow the drain the source voltage, okay. So that is why whereas the current is coming here, but since you are keeping VDS VSD in this case as minimal as possible, and hence there is no dissipation in this particular circuit. So this is what an adiabatic operation. So you can implement any function for that, not only inverter and NAND and whatever function you want to implement. This is the principle of operation, okay. Now if you see here, this is again an inverter which has been implemented. In this only A is been shown here. Now if you have to implement an NAND, okay, I can put one more transistor in series with this, right? If you have to implement an OR, I can put one more transistor here, and I can put it as B, then that will become A or B out here, right? So if it is NAND, I can put these two in series. So all functions can be implemented like this. Right. Now what is happening is, now if you see here, the clock initially I have given A. Again all the signals in an adiabatic will be, it will not be steep signals, right? It will all be slow ramp signals, okay. So now if you see here, this is A has gone high. Initially this clock is 0, right? So this A has gone high out here. When the clock is going high out here, since this is an NMOS transistor, if you see, okay, this is an NMOS transistor, this is not an PMOS, right? So A is high. So when the clock is going high, so this node will try to charge from here to here, right? So this node will get charged from here to here. So this is an similarly this is A bar, so this node will not get charged out here. So you will find this node is getting charge from here to here. The output is going high. As the VDD is going high, the output is also going high. Okay, that will also since there will be 0 out here, this PMOS also will be getting switched on. So this also will charge it to complete VDD, right? So this transistor also will be charging this node. So these two transistors, this NMOS and this PMOS together will charge this node to VDD in a slow fashion, right? And during this phase, you will find there is some positive current which is flowing, okay, into the circuit from VDD. From the VDD, if I plot, there will be some positive current which is flowing. Okay, this will be obviously this current will be much lesser than the currents normally you have in the static circuit. So you will have some current which is flowing out here. So this node will get charged out here, right? And when the VDD is going back, now after the evaluation phase, okay, after the evaluation phase, the VDD is again once it is evaluated, the clock signal goes low. Now clock means the VDD is here clock. Okay, when the clock is going high, the charge which is accumulated here again through this PMOS, okay, goes back into the clock circuit. So if you see here this circuit, but since it is an PMOS out here, right, it cannot transmit a full 0, so you will have some residual voltage available at this node. Okay, so before the next cycle, that residual voltage needs to be discharged. So you have two discharge capacitors. Once you give a pulse out here, this residual voltages also will come to 0 out here. In the next cycle, if you see here, A bar is going high, right? A bar is going high, so this node will get charged to 1. Okay, so every time when the clock is going high, depending on whether A is high or A bar is high, the output node will get charged accordingly to VDD. Okay, through these NMOS as well as through the PMOS transistors. Okay, and when the clock is going low, the charge which was accumulated again goes back to that circuit. Okay, so we will be able to recycle that charge. That I am going to explain in the next cycle, in the next slide. Here what we need to understand two things is, one, the VDD is ramped up slowly, so there is no adiabatic power consumption in the PMOS transistors, okay, because it is ramped up slowly. And the second thing is, whenever, so you will find here there is a negative current out here, like when the clock is going low, whatever charge is accumulated here, it goes back to the circuit, to the tank circuit. Okay, so it is known as a charge recovery. So the energy is again recovered back. So that is also happening in this particular circuit. Okay, so since this VDD is ramped up slowly, you don't have dissipations in the PMOS. Okay, the third aspect which we need to remember is, since it is an PMOS out here, suppose it is charged to VDD, while it is getting discharged, it will not get discharged to 0. It will get discharged to that VTN of the PMOS. That much will be retained at these nodes. So during the next evaluation phase, that could be a problem. So you have to discharge those two nodes. So you have this M5 and M6, two NMOS, where you give a discharge pulse, and so that will be brought down to 0. Okay, is this operation okay with all of you? Okay. So now if you see, I said the charge is going back to the circuit, right? So where is it going back? So generally you have the for the clock, for the VDD, you have this kind of circuit. So you have an VDD, then you have an L, and then you can have an C. Okay, if you don't have a resistance here, resistance is not, you are not going to put a resistance. It will be a stray resistance, the parasitic resistance, which will be there because of the inductor and the layout issues, right? So if I consider an ideal situation where R is equal to 0, in that case, if I just put VDD, L and C, then it will start on oscillating, right, like this, right? You will have an oscillator. Okay, the frequency will be depending on the L and C, right? So it will continuously oscillate. So that oscillatory signal I can give it at VDD. out here, right? So during the positive going cycle, this charge from here will go into the circuit, and during the negative going cycle, the charge again from the circuit will be brought back into these capacitors and inductors. So I can recover back this charge. So once I give VDD here, if there is no resistance at all, then this can continuously oscillate until infinite time, right? But because of stray capacitances and stray resistances which come into the circuit, because of the inductor and layout, this particular circuit, and also we are not able to, whatever charge we are giving into the adiabatic circuit, we are not able to recover back 100% of that. Some of that gets blocked in the circuit because of this PMOS out here, right? So some charge is getting, so 100% charge is not recovered, so some charge is lost there, and also because of this resistance also, some heat and some energy will be dissipated as it. So this will be a damping signal. Actually it will go like this, and then it will slowly it will it will die down. Okay, just to prevent that, you have an NMOS here, where you can give a regular pulse out here. So whenever you give the pulse here, and a high current from the source will flow like this, right? So once it, so energy comes into the circuit. So once it gets switched off, so obviously this current cannot die instantaneously, right? Because it is an inductor. So that energy gets stored into the capacitor. So this way, by giving small pulses through an NMOS out here, we are able to continuously a small amount of energy is being taken from VDD. But overall, if you see, as compared to the static circuit, this is generally oscillating. Only a small amount of charge needs to be taken from VDD periodically. Okay, so at say 1 kilohertz or lesser than that, some small amount of charge needs to be recovered into the circuit because of the losses which are not under our control. But overall, if you see here, adiabatic circuits have a much lesser power consumption than the corresponding CMOS. Okay, now the only issue out here is you need to allow this VDD and the V out to follow each other as close as possible. So you can't have it two operating in yeah, it is like a power supply boost circuits. Yes, correct. So you the thing is, we need to allow clock and V out to follow each other as close as possible, and for that reason we generally the adiabatic circuits work in the range of 100 megahertz, not more than that. So if you go for higher frequencies, then you will find that this adiabatic circuits won't work fine. So this was some study which I had done in one of my papers, in which this was static CMOS circuit power consumption as compared to that of an CMOS this orange one. This green one was with another circuit which I had proposed with TFETs. Okay, so that will not discuss out here. So if you see between the orange and the blue line, so there is a lot of savings in the power when we are using adiabatic logic. Okay, so this is one of the logics which are used. Adiabatic logic is used in many applications these days, especially for IoT networks. Okay, where you have a limited onboard power supply. Okay, so let me show you some simulation based on this also. Right. So this is an adiabatic circuit. This is an inverter. To compare with respect to an inverter, since in adiabatic I am going to get out and out minus both, I have cascaded two inverters here to get out and out minus. So I have put the load resistance. Let me put it as 10 femto. Okay, sorry, 10 femto. Okay, and let me put this as 50 nano. So let me plot the clock, input A, output minus, and also the current which will be drawn from here. NMOS discharge logic voltage. No, because you have to pull it down to 0. So NMOS will pull it to 0 properly, right? So that is the only reason. Here I have not shown the discharge signal out here. Okay, that is the reason I have left it. I can give a source there and discharge this output node. I wanted to show there will be some residual voltage there. Okay, let me sweep it for. So if you see here, A is 1 here, right, and the clock is going high out here in this case. So the output is also going out here. It is reaching VDD. While the clock is going low out here, the output is coming here. So it is not coming to 0 out here. If I put a marker out here, around 274 millivolt is residual voltage which is available here, right. So that needs to be discharged. So as of now I have not given the discharge circuitry. So this just to show that okay, this voltage, the entire charge will not be recovered back into the circuit out here. Okay, also thing to be noted here here you have a positive current of around 250 nano ampere. This is the current coming from the source. Okay, where is this circuit? This source I have plotted from this source. So if you see here, so this is a positive current out here, and when the clock is going low, I have negative currents. Okay, so that means whatever charge came from the source is going back to the source. Okay, so obviously not 100% is going back, but a considerable amount of charge is being pumped back into the source out here. Okay, here here I have not shown the clock recovery circuit. Okay, I have just shown the basic CMOS circuit. Here I have used a source out here. This will be a tank circuit out here, clock recovery circuit. So instead of that, I have just shown a voltage source out here. Similarly, I have not put a discharge pulse out here, and that is the reason this voltage is not going to 0 out here. Okay, so this is how adiabatic circuits work. So here what we need to note is here, okay, this is first of all the current. If you see here, the current is coming from the circuit out here, and the current is going back into the circuit out here. So the net power consumption will be negligible. Okay, we can even check the power also for that. Let me undo that, save all. right? If you see here, the power for the adiabatic circuit is it's showing almost 0, whereas if I see the power for the static CMOS, I have given the same frequency there. It is coming around 21 nanowatts. Okay, so if you see here, the power in the adiabatic circuit is almost negligible as compared to the CMOS. So CMOS, it is around 21 nano, right? So that power, if you see here, this circuit here the power consumption is around in nanowatts, whereas here it is coming almost 0. So we can do these things in LT Spice also. You can do that. You can do these simulations. Okay. Anyway, so so you can make an two. Can we check the transfer power? What is tran power? I have actually what I have done is, since I have placed both the I have placed both these circuits in the same schematic. So I have just named this particular source as adiabatic and this source as static CMOS, and then because if I do the trans, it will come the total power. So now I am checking for that device power, the power which is consumed from this particular source, static CMOS. Here this source static CMOS, and this source I have named it as adiabatic. So I am checking those powers. So here I am getting it as 21 nanowatt, and here for adiabatic I am getting almost as I am getting it as 0, right? Because if you see here, if I see this plot, here power you have a current coming from the source. Here in this case, when the clock is going low, you have the charge being pushed back to the source. So that is the reason the net power which is consumed is coming out to be 0 out here. Okay, so that's all for today. In the next class we will take on with a past transistor logic. Okay, thanks a lot.